Good morning, friends and dear students. It gives me immense pleasure to be here for my course, Flight Mechanics or Aircraft Performance. As of now, this is my 10th lecture. 9th lectures already I have completed, which covers the basics of flight mechanics like lift theory, drag polar, thrust required, power required, minimum velocity for the thrust required, minimum velocity for the power required, relation between lift and the velocity, at what maximum velocity you can fly, at what minimum velocity you can fly. Like this I have already covered. I have also covered the basic concept of the lift and the drag in my first one or two lectures, which it is very, very important. Today I am going to take the topic excess power and absolute ceiling. You know that I have discussed as of now how much power is available and how much power is required. Same way, how much thrust is available and how much thrust is required. So if we talk about the required is from the aircraft itself. Due to the drag of the aircraft, how much force is required to counter that drag. That is called the thrust required or the power required. But how much engine is able to produce the power or the thrust by the ignition of the fuel, by burning of the fuel, and by the different processes at the exit for the jet engine and at the shaft for the IC engine, propeller aircraft, how much power it can give maximum is called the power available. We have also seen in our previous classes that we will see here that topics are excess power, power available, power required, effect of altitude, absolute ceiling, service ceiling. Very, very important these 2 points to understand the concept of this service ceiling and the absolute ceiling of the aircraft, and this is directly related with the power available and the power required. Same way, if it is the jet aircraft, it is for the thrust available and the thrust required. So, introduction to excess power. Excess power of any aircraft is the difference between the power available and power required by the airplane. If the airplane has more excess power, then it can climb and do all maneuvering very easily. So if I draw this is the power required, and this is the power available. So the difference between this and this is the excess. So as much you have this value high and high, that much climb and maneuvering your aircraft can perform. As it is falling down like this is falling down like this is like this. One situation will come that time, this both will be same. If you see, one situation may come that this is the power available. As you go above the height, this is the power available, and you may get like this power required. So this is the point, this is the highest altitude where your aircraft can go. Beyond that it cannot. So this we are going to understand by the help of, and zero climb will be there. In this point, when PA is equal to PR, zero climb, that altitude is called the absolute altitude. Means your aircraft cannot go 1 inch beyond that altitude. That is called absolute altitude. So we have find the minimum thrust required velocity and the minimum power required velocity as given. So VTR minimum is equal to 2W by S divided by rho under root CD naught by K, and for the power minimum 3 CD naught by K. For cruise flight, message is clear for the aircraft designer that I need to fly at TR minimum CL is such that CL is equal to under root CD naught by K. So this is the CL. So this CL is equal to under root CD naught by K. If W by S is less, VTR minimum will also be less. Designer will select wing loading W by S for a transport aircraft, where W by is very important for the fighter aircraft, because maneuver is most important parameters. Accordingly, W by S will be chosen. Now the thrust available. Thrust produced by the engine is known as the thrust available, TA, and the thrust which required to counter the drag is called the thrust required. The difference between TA and TR is called the excess thrust. Thrust required is almost constant for given altitude and outside ambient temperature, shown in the figure. This you can see here. The difference between this red line, this is the TR and this is the TA. So we can see that the point 1 and the point 2, when TA and TR are intersecting. So here 2 points, if I extend this thing, it is the point 1 and this is the point 2, where TA is same. First I will discuss about the point 2 is the point where maximum velocity can be achieved. This is also statically stable in velocity. As the system goes above point 2, TA is not sufficient. So if you go here, it is 2 dash. If you go here, then what will happen? Here TA is not sufficient. Power is not sufficient. It will come back here. So the tendency of beyond this thing is to give the stability, will reduce and tends to come back to its point 2. If it is at less than point 2, TA is greater than TR, aircraft speed will increase and will go to the point 2. So this point 2 is a statically stable point. But if you talk about the point 1, is stall point velocity, it is called V stall. Here is statically unstable. It tends to go away from the point 2, point 1. So here V stall is equal to under root 2W by S rho CL maximum is greater than V stall. So always this thing should be greater than stall, and this is the CL maximum versus the stall speed. So stall angle. So it should be in this condition. Now power required. I will discuss about the power required. We have already, as we know that the gap between the PR, power required, and the power available is the excess power. How we can add the value for this to aircraft performance? Okay, so what we can use this PR and PA for the aircraft, for a designer? How? What the designer will understand by that. So here we have an aircraft which is moving with a velocity V, and the thrust is the T in the direction, gamma is the flight path angle, L is equal to lift here. This is the gamma is a flight path angle, and V sine gamma is a rate of climb of this aircraft. So we will see the equation of motion for the climb. T minus D minus W sine gamma is equal to m dV by dt. For the static performance, this dV by dt is equal to 0. So T minus D minus W sine gamma is equal to 0. We can write is T minus D by W is equal to sine gamma, and this sine gamma you can find out the flight path angle by this flight path angle using this equation, and if we multiply by V, so here TV dV is equal to TV dV by W is equal to V sine gamma, and this V sine gamma is a rate of climb. Here we have already shown TV is equal to power available dV is equal to power required, TV minus dV is equal to excess power, and V sine gamma is the rate of climb. So here we can see that TV minus dV is equal to excess power. So TA minus TR. So rate of climb is equal to excess power divided by weight. So this is the relation for the excess power and the rate of climb. V for maximum rate of climb. So now what is the velocity? What velocity for the maximum rate of climb? That is our question here. At what velocity we have to fly such that the aircraft will have more rate of climb? We all engineers, especially aeronautical students, should understand before they start making the RC plane. These all things you can do in our wind tunnel. Wind tunnels is available with us, very good wind tunnel. All type of measurement we can do it. Try to implement this type of ideas and make the project, publish the paper. When aircraft fly in such a speed, when excess power is maximum, will give highest rate of climb. So if we fly at this point where excess power is maximum, this speed is speed for maximum rate of climb. The speed V is speed at which the aircraft maximum excess power is available. If fly in this speed, the rate of climb will be the maximum. Power available, PA is sufficiently available, and hence maneuvering of the climbing can be done. So this is the speed for maximum climb, where maximum excess power is available. Let us revise again. So what is the cruise? It's an unaccelerated flight. Wings should be in the level flight, altitude fixed. So it is the aircraft in the same speed it is moving. Wings are straight and level like this, and the height is same. The height is remaining same. This is called the cruise flight. So we know that thrust required is equal to W by CL by CD. To have the minimums TR, CL by CD should be the maximum, and CL is equal to under root CD naught by K for the thrust required. At high speed, CL required is lesser, so induced thrust also will be lesser. So this CD is equal to CD naught plus KCL square. For the level flight, lift is equal to weight. This is the half rho V square SCL. So this CL is equal to 2W by rho V square S. We can calculate the CD as CD naught is fixed and K is given. So we can find out the CL, we can find out the CD, weight is given. So you can find out the TR. So how much TR is required, we can find out. Power required, you know that power required is equal to TR into V and W by CL by CD into V. V is equal to under root, this we have already done. PR is equal to W by CL by CD. And here you will see that PR is directly proportional to CL to the power 3 by 2 by CD. To have the power required minimum, CL to the power 3 by 2 by CD should be maximum. Lift required during the climb. How much lift is required? It is L is equal to W sine gamma. For the cruise, it is L is equal to W. So CL climb is equal to 2W by rho V square S into cos gamma. So CL cruise is equal to 2W by rho V square. So here induced drag of climb is lesser than the induced drag of the cruise. Hence power required is less during climb. dV is less in climb than the cruise. So power required is less during the climb. Comparison of the propeller and the jet engine. So if you see here, PR for the propeller engine, this is the PA and this is the PR. It is mostly like this, power required. And if you see here, for the jet engine, excess power is very less here. So accordingly, the excess power is less, excess power is more for this type of engine. Effect of altitude on the power. Now we will discuss about the altitude, this rho, how much it is differing. At sea level, CL will be the constant and the velocity at the sea level, that is V naught is equal to 2W by S rho naught by CL, and the PR will be 2W cube CD by rho S CL cube. At the same altitude, V altitude is equal to 2W by S rho altitude CL, and the PR is equal to 2W cube CD square by S CL cube. So comparing this, so V altitude is equal to V naught under root rho naught by rho. But this rho naught will be always greater than the rho. So PR at altitude is equal to P naught under root rho naught by rho. This shows that in the need a higher velocity to get same condition if going to higher altitude. So if you want to fly, so that need higher velocity to get same condition if going to higher altitude. So if you want to fly at higher altitude, you have to fly at higher speed. As we go up and up, density reduces, the power available decreases and power required increases. So power required increases. So here this concept of absolute and the service ceiling. So it is for the normal case. As you go up, this PR will go up. You see it is going up, and sometimes you will reach like this. As going up and up, power available reduces and power required increases. So this PR is going up and up. It was here, now here, and now here. And this is falling down, and falling down. So at some altitude, then is equal to PA and PR is known as shown in the figure. There is a zero excess power and aircraft no longer is capable to climb. This altitude is called the absolute altitude. So the altitude at which power available and the power required is equal. Beyond this, the rate of climb of the aircraft will be zero. That altitude is called the absolute altitude. Next is service ceiling or absolute ceiling, we have discussed before. Now service ceiling. Service ceiling is that altitude till aircraft maintains 100 feet per minute rate of climb. So this ROC, if it is up to 100 feet per minute, then it is a service ceiling. In this aircraft will be operating. This altitude is less than the absolute altitude in which there is a zero rate of climb. In service ceiling, aircraft can operate and do maneuvering, but at absolute ceiling, no maneuvering is possible. Only cruise flight can be performed. So if you see here, this is the rate of climb and this is the altitude. So at this point where the rate of climb is equal to zero, this is called the absolute ceiling. And at the point where rate of climb is 100 feet per minute, if you extend this thing, this height is called service ceiling. In this 100 feet per minute of rate of climb is possible. So that is the difference. In absolute ceiling, you cannot do any maneuvering. Only the cruise flight is only possible. But in service ceiling, all type of maneuvering you are able to do, and your rate of climb is 100 feet per minute. Next lecture, I am going to discuss about point mass model, modeling of the CL, dimensional analysis of the lift. So these are the points which I am going to discuss: point mass model, modeling of the CL, dimensional analysis of the lift. References are Anderson, Aircraft Performance and Design. This is the one book which mostly we are referring. Another is SL by ME, Aircraft Performance, Theory and the Practice, AIA Education Series. Any questions, you are welcome to ask. My email ID is ydwedi@gmail.com. In this, you can mail me or you can comment. Please do like and subscribe this channel, and be tuned for my next lecture. Very, very interesting about flight mechanics, about different other cruise, climb, maneuvers and all things we will be discussing in the next few lectures. Thank you very much for the joining. Till then, goodbye and see you.
Like, share and subscribe. Hit the bell icon for more updates.